Okay, thank you very much for inviting me. I was really hoping to be there in person, which might still happen on Thursday, but we'll see. So far I haven't had much luck getting to London. But so the main goal of this course will be to explain the recent proof of the universal optimality conjecture in 1824 dimensions, the conjecture of Kohn and Kummer. And so basically that part of the story will be a little bit of it I'll tell today. So I'll give some background, and I will explain basically what the conjecture is and what the main new ingredient in the solution was. And then so half of this course is basically a gentle introduction to modular forms, because the proof of the universal optimality conjecture so it requires surprisingly little geometry and surprisingly a lot of modular forms. So if you are already familiar with the classical theory of modular forms, most of what I'm going to talk about today, tomorrow, and on Wednesday will probably be not new. So the interesting stuff then will happen on Thursday and Friday, when I will actually talk about the proof of the so-called Fourier interpolation formula. So that's the main ingredient in the proof of the universal optimality conjecture. And then, so that will take me Thursday and Friday. But before that, this course will be mostly an introduction to modular forms. So if you've never worked with, or if you just heard about them but never seen them, this hopefully will give enough background for what will happen on Thursday and Friday. Okay, so but today I'm going to talk about the universal optimality problem. Well, the universal optimality conjecture, which is a conjecture about energy minimization problem in the Euclidean space. So I will start with that. So you've already heard this morning some things about energy minimization, potential energy minimization on compact spaces. So, well, our problem is non-compact, but it is, on the other hand, flat, so we don't have any problems with curvature. So what the main object of the story is the potential energy. And for the potential energy, well, I want to fix some basic notation for what are the configurations we're looking at. So basically, we're interested in closed discrete subsets in Euclidean space. So this will be what I will call configurations. And in principle, one also is interested in some subclasses of configurations for which certain densities are well defined, but that will not be a big problem for me. So there's two, and so the other part of the story is a potential function, which is just a function on positive reals, taking real values in principle, but almost all the interesting functions I will talk about will take values again in positive reals. And so this is the potential. And the quantity that we're interested in minimizing, so there's two parts. So here it's not just enough to say we want to minimize something. So first, there's some trick in actually defining what we want to minimize. So you would imagine that the potential energy of our configuration would be something similar to what happens in the compact case. So we take basically sum of all potential energies of pairwise interactions between points. Except, well, this doesn't quite work. So mostly we're interested in infinite sets, C. C is infinite. I mean, one can ask this for finite sets, but then one needs different kinds of normalizations. So this doesn't quite work well. So what we do is we actually cut it off. So CR is just by definition C intersected with the ball of radius R around 0. And so what we do is now we divide, so we take summation over these points, sorry, and we divide by the number of points in this kind of truncated set, truncated configuration, and then we take the limit as the size of this truncation goes to infinity. So this is the basic quantity that we're interested in. So E of Cp is a so-called lower P energy. And so the other thing is that because we're now in the non-compact setting, so this configuration C, so for example, we could think about P, for example, P being the reciprocal of the distance. And then, well, the problem is the minimum of this energy is kind of boring because you cannot make your configuration blow up. So you make, right, just rescale it by a large number. And then all the distances decrease and the energy decreases. So this will automatically make your energy smaller. So we want to have kind of some analog of number of points in the compact case. And in this setting, it's given by the density. So density is, well, the limit in this case, I mean, it's the upper limit of, well, since I already introduced this notation, of the truncated configurations normalized by the volume of the balls that we're truncating with. So what this, again, as R goes to infinity. So what this is, so this is this quantity rho of C is, it's just the average number of points per unit volume. So this is what the intuitive definition is. Okay, and so here, I mean, there are these lim inf and lim sup. So basically, in the rest of what I'm going to talk, I mean, in the rest of this course, I will only talk about the case when C is a periodic configuration. And most interesting questions are completely open for periodic configurations. So then this, we can remove lim inf and lim sup in the above definition. We just take the usual limits. And in fact, so what is a periodic configuration? I will say a few words more about that later. But for now, it's a union of a number of cosets by a lattice. Where lambda is some lattice. Oops. Lattice in RD. And so, I mean, if you don't remember what a lattice is, I will remind that a bit later. So, but for now, so what's important is the lattice has co-volume. So this is the volume, so equal to the volume of fundamental region for the lattice, which can be a parallelepiped or a Voronoi cell, doesn't really matter. And so this co-volume is directly related to the density in the following way. So the density of a periodic configuration C is equal to the number of cosets divided by the co-volume. So that's very nice and easy. And again, the energy for periodic configurations, you don't have to do this truncation business. You can rewrite it in a much nicer way, but I will do it a little bit later. Okay, so the problem, so now I can formulate the problem that we're looking at, the energy minimization problem. So we want to minimize the energy among configurations, so for fixed density of configurations. Okay. So, so this is a very general problem. Well, the main problem is I haven't said anything about what kind of function. So this was essentially arbitrary. And in such generality, there's really not much hope that one can solve it for large classes of I mean, in many situations. So basically, we will cut off the class of functions, potential functions, very drastically very soon. But so before we do that, I want to relate, since this energy minimization problem is directly related to this famous sphere packing problem. So so I want to talk a little bit about that. So what is the sphere packing problem? Well, in our notation is it's the following. It's a similar type of optimization problem. So sphere packing asks us to, well, we want to maximize the density over all configurations which have a certain property which it says that they are sphere packings over all C such that X and Y have distance at least 2 for any 2 non-zero points in C, non-equal points in the configuration. And so, so how it is related to the energy minimization problem? Well, it actually is related in several different ways. So one way, a very naive way, is we can just define a very silly potential, which takes value 1 if the distance is less than 2, and the value 0 if the distance is at least 2. And then the energy of a configuration with respect to this potential is 0. Well, here one has to be at least a little bit careful, because it's not true in general that this is a sphere packing if the energy is 0, but it is true for periodic, so for periodic C. So it's a little small problem with this reformulation. And so basically, if we have to solve the energy minimization for this potential, we basically have to solve the sphere packing problem. And the sphere packing problem, as you probably all know, is kind of it's very, so there are many guesses that we have for small dimensions for what the best sphere packing is, but there's not that much that has been proven. And until recently, the list was very short, but it was so due to the work of Marina Gwiazdowska, that was extended by 2 dimensions in 2016. So basically, the state of the art, if you want a complete solution of the sphere packing problem, so let's do a small table. So have dimension D, a configuration which attains the best sphere packing, and then, well, when it was proven. So dimension 1, well, the best thing is the integer, so it's kind of boring, or I mean, the way I set it up, it's actually 2z, but let's ignore that for now. I mean, this is trivial. So dimension 2, it's the so-called the hexagonal lattice or the triangular lattice. So it is a root lattice of type A2. And this is, well, there's some disagreement, I guess, between the experts on who got the first rigorous proof. So the first proof that appeared is due to Ture. It's from 1890. And then there are some actual proofs. So the proof that he gave was not rigorous enough, but there are proofs that basically use his ideas that were given by people in the beginning of 20th century. But there's also the proof which everyone agrees is correct due to Feuerstadt, who actually proved a slightly stronger statement. So this is around 1940. Okay, so dimension 2 is, well, it's difficult, but it has been known for a long time. Dimension 3 is a famous Kepler conjecture. And so here the answer is, well, it's again a lattice, but in fact, it's not the only solution. So it's a lattice of root type A3. And here the proof is due to Hales from around 1998. And it's again due to Hales and plus a lot of other, well, Hales and a lot of other people from 2014, if I'm not mistaken. So both proofs are heavily reliant on computers, but in different ways. So the original proof is relying on a lot of numerical calculations done on a computer. And that's why some people don't completely believe its correctness, because it cannot be verified by anyone. So you have to assume some trust in that the floating point calculations on your computers are all correct. And then the proof from 2014 is, again, it's not readable by a human, but it is at least it's verified on a computer. So it's a proof checked with a formal proof checking system. So it doesn't rely on some floating point calculations, but it's still not humanly understandable. So in principle, one would expect that the further down the list you go, that the more difficult these problems become. But then for some strange reason, there's some dimensions where things behave completely differently than in other dimensions. So in dimensions 8 and 24, there are there are guesses in the intermediate dimensions for what the best packing should be. But in dimensions 8 and 24, there is actually known to be the case. So, so in dimension 8, it's the E8 root lattice, and in dimension 24, it's the Leech lattice. And so in the first case, this is the work of Marina Gwiazdowska from 2016, and then it's the same, almost the same week. So it's a group of 4 or 5 people, so including Marina Gwiazdowska. So it's Henry Kohn, Abhinav Kumar, Steve Miller, myself, and Marina. So and this is basically what we know about the sphere packing problem. I mean, we know quite a bit more, but if you want to have exact complete solutions of what is the optimal configuration in some dimension, then this is the complete list. So in dimensions 4, 5, 6, 7, well, at least among lattices, we know what the best lattices are. And but they're also conjectured to be the best optimal. So the conjectures, conjecturally, sorry, can't write. So these are the D4 lattice, D5, although here I think it's not unique, E6 and E7. So these should be optimal among lattices, so this is known, optimal packings. And it is known that they're optimal lattices. And in dimension 9, there's something very bizarre going on, where there's continuum, there's continuous families of what people, sorry, best packings. And I'm not sure like how strongly people believe that these are all optimal, but that's as far as I know, that's the current belief. And in dimensions, there are some sporadic results between 10 and 24 for what people believe are the best packings, but in general, as soon as you go to high dimensions, we don't really have much confidence in whether the answer is well, likely to be correct or not. So I think in these intermediate dimensions, people more or less believe that the answer should be the way it is. But I'm not sure, even in dimension 9, this is kind of very optimistic conjecture. Okay, so but none of that is proven, so these are all very difficult conjectures. So going back to maybe I should say so this okay, so here optimal lattice packings are known, which is due to the work of Korkin and Zolotaryov. Sorry, I have no idea how to write this in Romanic, but and this is dimensions 4 and 5, and dimensions 6 and 7. Well, also dimension 8. So this is due to Blichfeld. Dimension 6, 7, and 8. And what's kind of annoying is that this was done, I think, end of 19th century. I mean, this was done around 1940, as far as I remember. And dimension 9, in dimension 9, we don't even know what is the best lattice packing. So in dimension 9, even among lattices, sphere packing is not open. Okay. The best packing is not known. Okay, so much for the sphere packing problem. So I'll just the reason I was talking about this is just I wanted to give some ideas to how difficult this problem can be. So in fact, it is more difficult than this might suggest. So let's go back. So go back to the energy minimization problem. So other potentials that people are interested in, and this is I mean, it's not a complete list, are the so-called Riesz potentials that you've heard a lot about today, and also Gaussian potentials. And so for these potentials, the problem is even worse in the sense that, well, until recently, the only case where we knew optimizers for these potentials were in dimension 1. So let me explain a little bit of what is known. So dimension 1, well, so let's, because there's some freedom in rescaling these, I mean, in choosing your potential and rescaling things. So actually, it's convenient from now on to normalize the minimization problem to only consider configurations with density 1. So for these potentials, actually, it doesn't matter what the density is because it's scaling. It's not invariant, but it's essentially invariant. And for Gaussian potentials, well, it's not invariant. The problem changes, but you basically get again problem for a different Gaussian. So you can always fix your density of the configurations you're looking at to be 1. So in dimension 1, it's known that the integer lattice is optimal for all these and Gaussian potentials. And in dimension 2, so what was known is So C is, again, we kind of expect what the answer should be, so it should be the triangular lattice. And what is known for lattices, so if you only look at lattices, lattice configurations and you minimize energy among lattices, for lattices, this actually a series of different results for these potentials. It's a sequence of works, so it's not sure. Let me think. It's Rankin, Castles, Dyananda, and Enola. And I'm not sure if the order is correct, but it's sometime in the 1950s, maybe 1960s. And then for Gaussian potentials, again, so this is only for lattices. This is a result of Montgomery. Sometime in the 80s, maybe. And in fact, the Gaussian potentials result implies the other result as well, as far as I remember. Okay, so that is okay, but then, well, this you already heard earlier today that there is a conjecture, and it's completely open. So conjecture is that this should always be optimal for all configurations. So the A2 lattice is optimal for all Ries and Gaussian potentials. And I guess I should have said here that we only consider S and alpha positive. I mean, it's also expected to be optimal for logarithmic energy, but I don't want to define it now. So this is a conjecture, and actually in dimension 3, the situation is a lot worse. So in dimension 3, we don't expect, so no single, well, no, okay, so the answer depends strongly on the potential. Depends on the potential function. And so basically there are two lattices, so FCC lattice, which is also the best packing. So it's essentially the A3 lattice. And the BCC lattice. And the two things are supposedly optimal in opposite regimes. So this is not a best packing, but it's a dual to FCC. And so this should be optimal, for example, for alpha going to infinity, and this should be optimal for alpha going to 0. But in fact, for alpha, so in the Gaussian energy case, so I'm looking at Gaussian energy. So for alpha around pi, neither is optimal. So there are configurations which are beat both of them. Neither lattice is optimal. And so there's this kind of difference between dimensions 2 and 3, and again, you would like logically expect, not logically, but at least intuition would suggest that as you increase dimension, this gets worse and worse, but in fact, that's not the case. So there's some phenomenon that Kohn and Kummer called universal optimality. So basically, what happens in dimension 2 with the hexagonal lattice should happen more. I mean, it's not limited to dimension 2, but still it's a very, very rare phenomenon. So universal optimality, this is, well, the whole concept is due to Kohn and Kummer, as far as you know. So this is basically just what I was saying with words just now. So a configuration C, let's just normalize it to have covolume, to have density 1, is called universally optimal if it minimizes the energy for a large class of potentials. Well, here you can either say for all completely monotone, for all P completely monotone functions of square distance, or, well, this is one option. Equivalently, if you don't want to think about what complete monotonicity is, so you just require it for all Gaussian potentials. So just, but still, let me remind you. So what is P of R is a function of R squared, and then G is said to be completely monotone if and only if its derivatives alternate in signs. So the case derivative is either positive or negative depending on the parity of K for all, well, here K is an integer. Okay. So, I mean, of course, one can define this, but the interesting part is that actually, so what Kohn and Kummer did, so they came up with a very good bound, what people call a so-called linear programming bound for energy minimization problem. And their bound was somehow very good in certain dimensions, so good, in fact, that it seems to be that it can be made exactly, it can be made to match exactly the energies of something known. So this is the famous Kohn-Kummer conjecture. So in dimensions 1, 2, 8, and 24, well, these configurations, so the A2 lattice, the integral lattice, the E8 lattice, and the 24-dimensional Leech lattice are universally optimal. Okay, so this is, it's not quite what they conjectured. They conjectured something much more precise, which I'll explain in a moment. But what, well, so as I said in the very beginning, it is known that in dimension 1, the integer lattice is optimal. So this they have proved using their linear programming bound. So theorem, even though I've recently learned it's been known before them, but let me still call it the Kohn-Kummer theorem, that Z is universally optimal. Okay, so basically the goal of this course is to explain another theorem, which is due to the same group of people that did this sphere packing in 24 dimensions. So it's, I mean, it's the preprint is from 2019, but it will appear this year in Annals of Mathematics. So we proved two other cases of this conjecture. So lambda E8 and lambda 24 are also universally optimal. Okay, and so now what I want to do is I want to explain more about what was the actual conjecture of Comet-Kummer. So they didn't just say, here's a list of 4 dimensions, and then in these dimensions, for some reason, these configurations should be universally optimal. They actually gave a good reason for why this should be the case. So yes, so let me now explain a little bit. So first, maybe I want to spend 5 minutes actually defining these two lattices. So definition of E8 and the Leech lattice. So I expect that some of you are probably very familiar with this, but still let me do this and remind you. So basically, as I said before, all of these problems, I mean, they're formulated for some general discrete subsets of the Euclidean space, but really you're mostly interested in periodic sets. And I said what a periodic set is a set of cosets, is a disjoint union of cosets by a lattice, but let me just briefly remind you what the lattice is. So, so a subset of R to the D is called lattice. Well, if lambda is, so I will say, I will define it in 2 ways, so one very concrete and one very abstract, is a discrete co-compact additive subgroup. R to the D, so this is one definition, or if it's a set of the form A acting on the set of integer vectors, where A is a matrix in GLD. So most of the time, the interesting lattices are much more restricted than that. So what's usually people, well, so let me just say a few words. So the covolume that I already used, in this way, it's just defined as the absolute value of the determinant of A. And then you can also figure out from this description what the fundamental set, is A times the unit cube. I mean, you can take half open unit cube. And its volume is, of course, the determinant of A. And so there are certain properties. So basically here I said it's just a subset of R to the D, but R to the D, we don't consider just as a vector space. So R to the D is equipped with the inner product. And so, I mean, obviously, if we didn't say anything about that, then the whole theory of lattices would be extremely boring because everything is linearly equivalent to the set of integers, to the lattice of integers. But in this case, we actually restrict. So we're only interested in lattices up to isometries and sometimes up to homotopes. So this makes the whole thing much more interesting. And so the properties that some of the properties of lattices that we're interested in are integrality. So, sorry. So lambda is integral if all inner products of elements in lambda are integers. And lambda is unimodular. So here there's some confusion about what set of conditions are called which. So unimodular, I will just say if the determinant of, well, the covolume is 1, but some people require more. So they actually want it to be integral and have the covolume 1. And then lambda is called even. And this is a kind of a stranger notion. If all norms of vectors in lambda are even integers. Okay. And so, so the Leech lattice, so lambda, and the E8 lattice are even integral. Well, you don't have to say, in fact, even implies integral, which is a small exercise if you want. Even and unimodular lattices. And another thing I forgot to define here. So also there's something called the dual lattice. So for each lattice, we can associate its dual, and it's just the set of all vectors which have integral inner products with the points in the original lattice. And so in fact, every integral and unimodular lattice is automatically self-dual, meaning that its dual is equal to itself. So in particular, the E8 lattice and the Leech lattice are like that. And the fact that they're even, so they're even, tells you that, well, the set of squares of this of lengths of vectors over E8, it's contained in, well, the set of even integers. But in fact, so the same thing is true for the Leech lattice, except something even stronger is true. So there are no vectors of length 2 in there. And in fact, well, I wrote here an inclusion, but this is actually an identity. And so let me define what the E8 lattice and the Leech lattice are. So the E8 lattice has a very simple definition, which you can use it to actually verify all the properties that I mentioned above. Almost all except for this equality here, it's a little bit trickier. So it's a set of all vectors, well, which are either all consist of integers, integer components, or half integer components, such that the sum of the coordinates is even. So this is the definition of the E8 lattice. And basically just using this, you can write down a basis for this lattice, you can figure out the covolume, and you can prove that it is actually an even lattice. So this is much easier. The Leech lattice is notoriously difficult to define. Well, there is one way to define it, which is simple, but it almost doesn't tell you anything about the lattice. So it's kind of tricky. But let me give you, because it's a very beautiful discovery of convex form. So so what you do is you start. So how to define definition of the Leech lattice. So you start with something that actually is not a lattice in the sense that I described above. So you start with a Lorentzian space. So it's just a Euclidean space of 26 dimensions, equipped with inner product which is not positive definite. So, but I will let me denote it by still by dot product, but this is now so you think of x and y as vectors in this space. And then you take, so the way I write it, maybe let's not make it too complicated. So x times y is, so it's almost like the standard inner product, but then the last components you take this negative sign. So it has signature 25(1). And then, so what one does is the same way as we defined above the E8 lattice. So one considers a lattice in this space, something which people denote the second type of even unimodular lattice in the Lorentzian space, with indices 25(1), which is the same, it has the same definition as the E8 lattice. So it's just not in the Euclidean space, but in the Lorentzian space. So again, you take all vectors which are either all half integral or all integral with the sum of xi's even. And then inside this lattice, there is a there's very strange vector which one takes, which is it's just a vector whose components are all integers up to 24, so 0, 1, 2, so on 24, and then the number 70. And then, well, there's another vector similar to that, where you just permute the first two coordinates. And the defining property of these two vectors is that in this Lorentzian space, well, they're isotropic, and they have inner product -1. And this is kind of strange. So why would you care about this? So this is something called the Weyl vector, and I won't go anywhere close to explaining why it's called Weyl vector. And when dimension 24, so number 24 appearing here has the unique property. Well, it's almost a unique number with the following property that the sum of squares of the first n integers is again a square. So is equal to y squared for some y. So if you try to look at the set of integers with this property, well, it turns out that this contains exactly two numbers, and it's 1 and 24. And for some reason, this 24 corresponds to the existence of the Leech lattice. So I have defined these two vectors, but let me tell you about the Leech lattice. So the Leech lattice is the orthogonal complement of these two vectors. So you take everything inside this Lorentzian lattice. So you take every vector here, which is orthogonal with respect to this Lorentzian inner product to the vectors W and Z, and you restrict this non-positive definite inner product to that set, and it turns out that that is positive definite and actually defines the Leech lattice. Unfortunately, this definition is very hard to use. So if you even try to prove that it's well, you can more or less easily prove that it's positive definite, but if you try to prove that, for example, it doesn't have vectors of length 2, it's some complicated property which is not hard to see at all, but it's true. Okay, so maybe let's have a short break, and then I will continue 10 minutes.
Okay. So are there any questions so far? It seems like there are no questions, but so let's make a break, take a coffee, and maybe you can make yourself a coffee too.
Okay.
And let's reconvene in 10 minutes. Okay.
Okay, so let's continue. So I want to now describe the actual conjecture of Kohn and Kummer, and that is, well, more or less what I was starting with. So I was starting to talk about the linear programming bound. So what is the LP bound for energy. And so I will just formulate their theorem and then I will make some comments about it. So basically they have a way of producing lower bounds for the energy that you kind of, you get, so you produce such bounds from certain functions. So you start with a function. First of all, let me just briefly recall. So we will talk about functions defined on the space that we're looking at. And they don't really require this function to be that nice, but I will limit myself to the so-called Schwarz class, which means that f is, well, it's infinitely differentiable and rapid decay, and has rapid decay for all derivatives. For f for all multi-indices. Okay, so this is roughly what the Schwarz class is. So even if you don't like that, we will have a smaller class of functions that you will work with, which are all will be in Schwarz class. So basically what you do is you start with a certain function, and so the other kind of key ingredient is a Fourier transform, which I will just define. So there's many normalizations one can do, but this one's particularly convenient. Well, this is the Lebesgue measure of x. And and here x dot xi as before. So now forget for all the things I was talking about Lorentzian space. It's just, this is again the usual Euclidean product. Okay, so this is basically the setup, and their theorem is Kohn and Kummer. It's roughly based on a similar result about the sphere packing problem that was found earlier by Kohn and Elkis. And in a sense, if you just look at the proof of that result, you can kind of come up with this theorem as well, but still. So what you do is, so you start with a certain function, and like I said, I will assume that it's a Schwarz function. Such that it has a few properties. So we have a potential in mind. So we're interested in finding a lower bound on the potential energy. So we have certain condition involving the function and the potential. So we want the function to be maturized by the potential for all, well, for all points except at 0, because at 0 the potential might not be defined. And we also want the Fourier transform to be non-negative everywhere, which is the so-called positive. Well, this is what is the positive definite function, although it's a small subclass because we only look at Schwarz functions. And so whenever you have a function with these two properties, well, let's just continue. Let f be a first function with these properties. Then the energy, so for any configuration C, one has so the energy of the configuration, the potential energy with respect to this potential P is at least and it's bounded from below by the Fourier transform of this test function, or not test function, but this auxiliary function f at 0 times the density of the configuration minus the value of the function itself at 0. So this is their theorem, but I will actually append a small. So this is what actually a corollary of the proof of the theorem. So in addition, it's kind of it's a corollary that tells you that this bound in certain cases can be optimal. So if a configuration C is a lattice, and in addition to these inequalities, so in addition to 1, if you also have certain equalities, so if f of x is actually equal to p of x, not just less than or equal, on all the points of the lattice, on all the non-zero points of the lattice, and the Fourier transform, if it not just bounded from below by 0, but it actually vanishes at all points of the dual lattice, then this lower bound, so then C is optimal for P energy. So this lower bound is actually attained for P energy. And it's attained at C. And in fact, I mean, whenever you find a situation where these stronger conditions hold, you can actually say a lot about the set of optimal configurations. The only problem is that we have very few situations where actually this, first of all, is expected to hold, and second, where we actually know how to construct such functions f. And what I want to do is, so I will present the proof, because it's a small calculation and it actually tells you a lot about the problem. And maybe let me go to the next page. So let's assume, and actually, so I lied a little bit. So they proved it for periodic configurations, but the theorem is true for everything. So for periodic, so Kohn and Kummer proved this for periodic configurations, and Kohn later, Kohn and of course the island for all C. Okay, so and the proof is actually really simple. So, and I will only do the periodic case. So if you assume that C is a disjoint union of a few cosets, so I will denote them Vj plus lambda, where lambda is some lattice. Doesn't matter. And so you just compute the energy. And I didn't quite do this calculation, but you have to believe me that if you compute the P energy of a periodic set, you don't have to take all these limits and take some truncations. You can just write it as a double sum. So it's a sum over all pairs of cosets, and then you compute the summation. So you average out by the number of cosets, and then you compute a double sum over cosets. And the sum is basically you take, then you take the inner sum over the lattice. you take the energy of so you take kind of the interaction between 2 points, one in one coset and one in the other. And here, I mean, it's not, this is not quite the right definition, because some of these points might be 0, so we actually have to remove them, because we don't compute self-interaction between points, so we remove vi minus vj. Okay, so I mean, it might happen that vi minus vj is never in the lattice, but we don't assume it. So then what we do is we just rewrite this several times using certain properties, either the assumptions about f or some general properties of the Fourier transform. So first thing that we do is we actually use f less than or equal to p, or p is greater than or equal to f. So we just rewrite the same thing, but with f now. And now it's not f of absolute value, because f is actually defined on the full space. And now we just rearrange terms a little bit. So here we had this condition that the point inside the summation, we don't want this thing to be, so this, oops. So this we want it to be non-zero, because p wasn't defined there. But now we don't actually care, because f is defined everywhere, so we can make summation set simpler. So add all these points which are extra, and then remove a number of f nodes. So it's actually equal to, and if you compute how many times you get a 0 in here, it's actually n times exactly. So when you compute it with 1 over n weight, you get minus f at 0 plus 1 over n times the sum over sets. And now the summation doesn't have any restrictions, so we sum over the full lattice. And so the next step is you apply Poisson summation formula. So Poisson summation. And I will write it here, but I'm not sure if it's actually visible. So the summation over the original lattice, you can rewrite the summation of the dual lattice of the Fourier transform, and then the translation becomes the modulation. And so when you actually apply this here and rearrange all the terms in the correct way, you get 1 over the covolume here. So you get 1 over covolume, and now summation over the lattice becomes a summation over the dual lattice of the Fourier transform at xi. And then, so all these modulation factors, you kind of group them together and put them in the same, like group them all together into a trigonometric polynomial. And this trigonometric polynomial is actually very nice. It's just the square of something. Sorry, so now it's single sum. Okay, and then, so what you notice that here, every term is non-negative, and by assumption, so you know that f hat is non-negative. So you basically drop everything except the term at 0. Except, so this the term at 0 is multiplied by n squared, because this trigonometric polynomial has value n at the origin, and everything else you just drop. So you drop every term except the origin. And this actually, you kind of remember what I told you before, this is the density of the configuration. So this is the proof. And so this is the proof of the first part of the theorem, but also if you look through this chain of inequalities and look at where we actually used, I mean, where we could have lost something. So we only lose things in the first line or in the left line when we apply some inequalities. And here, so if you now do this calculation for the lattice lambda instead of the configuration C, so just plug in lambda in here. So all this stuff becomes much simpler. And here, so here you lose if P of X is not equal to F of X. So then you get some strict inequalities for X and lambda. And here in the left line, you lose something if F hat of psi is not 0 or some non-zero lattice point. So now if you look at these conditions, so they tell you exactly that you never lose anything in this calculation, so you actually get an identity. So yeah. So that kind of leads to the question, and this is a question which is surprisingly hard to answer. So when can we have both sets of conditions? So when do we have both 1 and 2? And this is the conjecture that actually Kohn and Kummer made. So conjecture of Kohn and Kummer. So the real conjecture, not the statement I said before. So they conjectured that their LP bound is optimal for D 1 to 8 and 24. The LP bound is optimal. So there is, in other words, there exists some function. So there exists a function as the properties 1 and 2. Well, one has to be a little bit careful because I was talking about completely arbitrary potentials, but of course this cannot, this cannot work for all potentials, but for Gaussian potentials that should work. For all alpha. Okay. So what happened? So dimension 1, they actually managed to prove using the theorem, and it's not a hard thing to prove. So dimension 1, this works. Dimension 2, unfortunately, this is very open. Well, it's still open, and it's one of the probably the most important open problem in the area. I don't know. Definitely one of the most important problem in the area. And so, I will tell you maybe on Friday or on Thursday, maybe more about dimension 2, so why it is complicated. But roughly, I can tell you now already. So what happens is that these conditions, they tell you a lot of stuff at points on the lattice, and they don't tell you anything else. And in dimension 2, the lattice doesn't have enough points to tell you something very strong about your function. And in dimensions 8 and 24, so the 2 gives a lot more information. So the equalities give a lot more information about F than in dimension 2. And in fact, we expect in dimension 2, there should be many like huge spaces of functions which have both 1 and 2. And in dimensions 8 and 24, the function that has both properties is essentially unique for every Gaussian potential. Okay, so let me just reformulate. So let's reformulate. Oops. What 1 plus 2 tells you if you want to prove that the E8 lattice is universally optimal. So we want, and then we want, let's take the potential to be Gaussian. So we want functions that are majorized by Gaussians. Oops, no. Which are positive definite. Well, for all xi. And so this is the condition 1, and condition 2 is so let's play a little bit dirty. I said functions, but let's just say f is a radial function. And in principle, none of the all of the conditions are radially invariant, so this is not restricting anything at all. So I mean, maybe I'll explain a little bit more later. So we also want this to happen whenever x is in the E8 lattice. Oops. And we want, sorry. And we want this to happen also. Well, whenever xi is in the dual lattice, we want this vanishing for the Fourier transform. But I already told you that the E8 lattice is self-dual, so this is the same set of numbers. And actually, so let me now say, I'll do some erasing here. So we said that f is a radial function, and in principle, the set of vectors of the E8 lattice is not very simple, but I already told you that the set of square roots, so the set of lengths is very simple. So let me just do some rewriting here. So for all n greater than or equal to 1. Oh, sorry, and here, of course, this was without 0, but since I'm erasing it anyway, it doesn't really matter. So, and I will abuse notation, and for radial functions, I will just talk about them as if they were functions in one variable. So this will mean the value of the function on the sphere of radius squared to n. And here I get e to the minus 2n alpha. And here again, I do some erasing. Oops. And I also have conditions at these points. So we can draw some pictures. So if you think what these functions behave like, so this will be a picture for f. This will be a picture for the Fourier transform. And so here is, well, let's think of a Gaussian. So this is e to the minus alpha r squared. This is radius. And so here our function should, well, we don't really know what happens at the origin, but we know that, oops, it worked. It should behave somehow like this. So here, the places where it actually agrees with the Gaussian should be square root 2, square root 4, square root 6, square root 8, and so on. And on the Fourier transform side, we just want some vanishing. So again, this is not, none of this is to scale, and the numbers are much denser than I'm drawing them. So this is what should happen roughly for the 8-dimensional optimal function. And so, but you see that because of this, we have both inequalities and equalities, actually the condition 2. So 2 implies a stronger set of conditions. So we have f at square root 2n is equal to e to the minus 2n alpha, but also the derivatives should agree. I mean, I'll just write the derivative at that point, but you know what p is. And the Fourier transform should also vanish to second order. And the derivative also vanishes. So this happens for all integers greater than or equal to 1. And so basically what happens is this problem I mean, it's, so in dimensions 8 and 24, this problem is really, it's on the boundary of being unsolvable, in the sense that this set of conditions is actually very hard. Well, if you don't know anything about the problem, it's very hard to come up with functions which satisfy such things. So because you have to control both function and the Fourier transform at certain points, and it's very hard to do. And what turns out is that actually this set of conditions is complete in the sense that it completely determines a unique function, and then the problem becomes in actually checking the first condition for that function. So let me tell you what the main kind of ingredient in the proof of the universal optimality is. So there is a theorem which we call Fourier interpolation. Well, Fourier interpolation formula, but it's very special type of interpolation formulas. And so basically there is a way to recover a function from just knowing these values. So the values at square root of even integers. So there is a formula, I'll write it this way. Sorry, actually, let me say a few words. So, so D is 8 or 24. There exists, so for all D in this set, there exists a collection of functions an and bn, starting from index n naught, and n naught is equal to 1 if dimension is equal to 8, and 2 if dimension is equal to 24, such that for any radial Schwartz function f doesn't have to be real valued, but whatever it is, one has following formula. So basically, it's what you would maybe naively guess from what I was telling you. So you take the collection of values at square roots of integers and square roots of square roots of even integers, and you just find some formula which reconstructs your original function. And well, the most natural thing one can do is to assume that the reconstruction formula is linear, and then that's what it would look like. But the real, the real point is that there is a way to fill in all the unknowns here. So let me write it down. So here, the head for bn head is the Fourier transform of the function bn, and an head is a function is a Fourier transform of an, and ans and bns. So here I didn't say anything, but they're also Schwartz and radial, so radial Schwartz functions. And so what this theorem tells you more or less is that if this problem 1 plus 2 has any solution at all in dimensions 8 and 24, then you only have one chance for it to work. And moreover, so the real point is, it's not just that there exist some functions that you can plug in to make this work, but that everything here is computable explicitly. An, bn are explicit. Well, to the extent that, yeah, to a certain extent explicit. So it's not that we have a simple formula describing all of them, but we have a way of computing them. And now I'm coming to the other part of the course, and are constructed using modular forms. I will say for the group PSL to Z, but that's not exactly true, but it's almost true. Okay, and so you see what happened is we have a statement which seems like a theorem in Fourier analysis, and really, so it's the surprising part about it is actually it's not a theorem in Fourier analysis. It's a theorem about something that's called modular integrals, and really it's a theorem about modular forms. So that's kind of one common property of modular forms. If you've never encountered them, like a universal property of modular forms is that they appear everywhere, all over mathematics. And so I don't know. I mean, in principle, maybe there are some questions for this part of the story. So from now on until Thursday, I will talk about modular forms. So I want to give some background for that, and then after we've laid some basic, after I've told you some basic things about modular forms and theta functions, I will come back to the question of how to actually prove this theorem, and then how this implies universal optimality. So this is a good place to maybe, I don't know if there are some questions to the geometric part or like optimization part of the story, then
Are there any questions?
here's a good point.
Actually, I have a couple of, maybe I have too many questions. So anyway, one question that maybe is instructive, you decide if the case of this theorem for the dimension 1 would be, does it have an analog for dimension 1?
This theorem.
Here, yeah. Radial is very... It
actually has a dimension 1 analog. So, and this is in principle, okay, there is an analog. It is what people call, it's not exactly the Whittaker non-interpolation formula, but it's almost that. So there is, yeah, so there is an interpolation formula. Formula for functions. Well, here it's an interpolation formula for radial Schwarz functions. But there is a formula for compactly supported, band limited functions, which serves the same role. So as this theorem serves in the proof of the universal optimality in 24 dimensions. I mean, it's a little bit technical to actually write it down, but there is an interpolation formula in dimension 1. And that was used. By Kohn and Kummer to actually prove. Oops. To prove universal optimality of Z. So it's roughly, it's something of this shape. So I will probably make it completely wrong, but there is a formula. Oops. And someone may correct me. I think it's but I'm not completely sure. Squared plus sum of something similar with the derivative. And some other basis function here. So I don't remember what it is. And so for f hat supported in the interval from -1 to 1. And so, but maybe someone can actually tell me what is, so I might be messing up. So maybe it's not even integers, but that's the general idea. And so what you kind of use this in a similar way to the way we use this theorem. So you plug in the values that you get from the like this optimality condition for the Kummer linear optimization problem, but you also assume that so the Fourier transform is not just vanishing at these points, or like the points that would correspond to the one-dimensional case, but actually they vanish outside some small interval. And so in that case, this actually gives you something which works. And that's why the one-dimensional case works. And there's some speculation about that there should be some intermediate space of functions for dimension 2, because there something similar happens where you have not enough information from these conditions, but I don't know. So that maybe I can explain more on Friday.
Okay. Okay. So more questions? Anybody? There is a question from that.
Just one other. You mentioned that there was another proof of universal optimality in one dimension that you recently that was before.
So unfortunately, I cannot hear very well, but maybe Mircea, can you give a microphone or
So yeah, can you hear me?
no, very, very faintly.
Go up front. There.
Okay. Okay, so the other question was Doug was asking, there is another proof you mentioned of universal optimality in dimension 1.
Yes.
And then the question was by which author?
Yeah, let me, if you give me 1 second, I can look it up. So just a second.
You can also answer next time.
Yeah.
I could also answer next time. That's maybe better. But yeah, so this is what we found actually in when we did the proofs for the submission. So there is I don't know if Henry knew it earlier than that, but there is a work by people. I would like to say mathematical physicists. So I will tell you the names next time. So actually, they also proved the universal optimality in dimension 1. Without, I mean, the proof is morally similar. So it's also using band limited things, and it's not explicitly stating it as a linear programming problem, but it's morally it's similar. So there is a proof which looks kind of different, but it really is. From what I remember, it's almost the same idea. So.
Okay.
So in dimension 1 and 1 dimension, so actually we expect in dimension 1 there should be huge collections of functions which have all these properties, not just band limited, but also Schwarz functions. But as far as I know, even in the Schwarz class, maybe there are no known constructions for now for functions satisfying all this in dimension 1. It's not maybe a terribly interesting problem, but in dimension 2, of course, we have much more complicated issues. So there, yeah, it's wide open.
Okay, so.
But I will like do my homework, and I will tell you exactly who proved the dimension 1 case. Maybe tomorrow.
Okay, thanks. Okay, there are no more questions. It seems.
Okay, so then actually I think it's kind of nice because I can tell you what modular forms are without telling anything about modular forms, and then tomorrow we actually start the modular form part of the course, and that hopefully I will fit that in 2 days, but we will see. So I will not. So yeah. So the point is, you'll have to be a little bit patient. So you will only see why modular forms appear here in a couple of days. But really, so more or less, it's I mean, it's a very useful thing to remember. And it's something that I learned from my advisor, that modular forms are everywhere. And so hopefully, so even if you're not interested in modular forms, and if you're familiar with them, of course, I won't tell you much, but if you have never seen them, it's always good to think about them. Yes?
No, don't worry. It was the computer is doing something. Sorry.
Okay, okay. But you still see something. Yes, I was just trying to say that it's a good idea to keep them in mind, because sometimes they tend to appear in problems that seemingly have no connection to them whatsoever. So what are modular forms? Well, okay, a modular form, and it's very hard to convince people that this is a object worth studying if you don't give any kind of applications. But the good thing about modular forms is they have so many applications, it's hard to list them all even in 1 hour. So modular functions and modular forms are related things. So modular functions are holomorphic functions on the upper half plane, which are invariant under the Möbius transformations with integer coefficients, and modular forms. So F is a modular form of weight k, and k will always be an even integer, except when I will cheat, and then we will have sometimes things which even have non-integral weight. But for now, just think of k as an even integer, and modular form is a function that satisfies this transformation property for all matrices in SL2Z. So you think of f is a function on the upper half plane and so what we also want f to be holomorphic, except, well, much of modern developments in modular form theory actually drop this assumption completely or partially. And another thing that we want is we want to have Fourier expansion without negative terms. So what you get is an expansion of this type, and Q is very commonly denoted, a common notation used for the function e to the 2 pi I tau. So you want a Fourier expansion which only has positive powers of Q or non-negative powers of Q for some complex number C. And actually, so it may not immediately be clear why one should even look at Fourier expansions. So why does this function have to be periodic? But actually this is, so if you think about matrix A, B, C, D is 1, 1, 0, 1, this tells you that function should be one periodic. And then it's an exercise to actually prove that any one periodic function has this expansion. So this is roughly the definition. So tomorrow I will do a more careful definition. And the nice thing about this is it doesn't tell you at all why one should study these objects. But fortunately, or I don't know, it just happens so that these objects appear all over mathematics all the time. And so just to give a few examples, well, so where they appear? Well, we kind of, let's start with the topic that we're discussing already. So in the sphere packing problem, so this is in the work of Marina. So it's not the most famous appearance of modular forms. So in the proof of Fermat's last theorem, in the work of, well, people usually only mention Wiles, but really there's a huge list of people involved. So Frey, Ribet, Serre, well, Shimura, Taniyama, Weil, a long list of people involved with that. I mean, what other striking examples can I give? I guess there's a proof of irrationality of zeta 3. So there is, this is a famous result of Apéry, but the proof, oh sorry, the proof I'm talking about is well, so Apéry's proof in principle has something to do with modular forms, but in a hidden way, but the proof is due to Fritz Böckers. So this is a modular proof. And there are a few other examples, for example, algebraic independence. Oops. Of pi, e to the pi, and gamma of 1/4. So this is due to Nesterenko. What else? Well, yeah, so maybe more number theoretic applications, but there's many more. But perhaps for this for the summer school, the main thing is this. And well, I already kind of spoiled that energy minimization, but it's these two developments are closely connected in R8 and R24. So just this is just some kind of set of things that I wanted to mention. So to give you some idea that modular forms seem to have many applications, and some of them are very surprising. And so tomorrow I will actually define what modular forms are, but already on the basis of just this rough definition, there's some exercises that I have prepared. So I don't know if probably there's a way to send them around participants by email.
Yeah, you can send them to us, and we are going to.
Okay, then I will do that, and then tomorrow I will restart somewhere around here and actually do a proper definition, and then we will work out what modular forms for SL2Z are. Okay.
Okay, thank you very much. Okay, so are there more questions? Okay, if not, well, then you can also write questions, and we make them reach Danylo for tomorrow, or you can ask them tomorrow.
Right? So also I should mention, so tomorrow we'll have one hour lecture and 1 hour exercise solving session, or question asking session. I don't know, whichever you prefer. So, okay. but like I said, so there are already some exercises for basically which don't use anything about the definition, about modular forms except the definition, and then you can also already look at them. Okay, so
okay, so send us everything, and we share it with the participants. Okay. So thanks, and then we reconvene in a